Assalamualaikum guys, welcome back to Chemistry World and I'm Wahaj Khalil. Today's topic of our lecture is the mechanism of alkylation of benzene in aromatic substitution reaction. We will also discuss some alkylating agents in the lecture. So stay tuned and watch the video till end. Thanks. Hello guys, welcome to Chemistry World by Wahaj Khalil and today's topic of our lecture is alkylation in aromatic substitution reactions. So first we have to see the reaction. Here we have a benzene ring plus, for alkylation agent we need an alkyl halide. It will also be our Br or high, where R is CH3 and it is alkyl group. We need Lewis acid as a catalyst, AlCl3 goes to, here we have R, so it is toluene now, plus HCl plus AlCl3. So this is the general reaction. As we know that there are 3 steps in aromatic substitution reaction for its mechanism. The step number 1 is making of an electrophile on which the benzene ring can attack. First of all, making of electrophile. So we take alkyl halide as an agent of alkyl group. So it reacts with our catalyst AlCl3. As we know that the electron pair on a chlorine attacks on Al of AlCl3 and AlCl3 becomes AlCl4 minus plus R positive. So this is our positive and it is our electrophile. The second step in aromatic substitution reaction is making of pi and sigma complex. Pi and sigma complex. So now we have a benzene ring and our electrophile are positive. As a nucleophile, this pi electron attack on positive of this R and make our pi complex, and we can represent it as follows. Here are positive. So it is a transition state. Pi complex is a transition state. Pi complex. It is a transition state, not available for a long time. And this pi complex will convert it into sigma complex intermediate. So it is an intermediate state here R, here H. Here we have a positive sign. So it is a transition state, so there is a resonance in its structure. This positive moves in this way. Here is our pi bonds. There is R and it is H. Now the positive sign is here, and this is our R and it is H. So these are the resonating structures of pi complex, but we can show it as a whole as follows. Because it is a resonating structure and it is conjugated, so we can represent it as follows. So it is our sigma complex. Sigma complex intermediate. So this is our second step, and now our third and the last step is removal of H positive from sigma complex. Removal of H positive. So it remove H positive from this H positive from this side to regain stability, to regain aromaticity and the electron pulling effect of this ring. And due to the presence of base, which is made in our first step, named as AlCl3 negative, it attacks on a H of this, and we can get our product, which is toluene in this reaction. It is R here, and plus HCl plus AlCl3, again AlCl3. The catalyst returned to its original position. So here the question raises why the sigma complex releases H. So there are 3 points. First of all, to regain aromaticity. The second one is due to electron pulling effect of ring. Pulling effect of ring. And the third one is due to the presence of base named as AlCl3, which we made in our first step, presence of base. That's why this H removes from the sigma complex. These are the 3 reasons. Instead of AlCl3 as a catalyst, we can also use more catalysts, but AlCl3 is here act as strong catalyst. We have other catalysts as follows. First one is AlCl3. If we don't like, we can use FeCl3. If we don't like, we can also use BF3. It is not just strong electrolyte. We can also use TiCl3. We can also use ZnCl2. Sorry, 2. We can also use SnCl4. So this is our list of catalysts in decreasing order of their reactivity. Polyalkylation is also done by other reagents. For example, alkene CH3 CH double bond CH2. For this purpose, this alkene is first attacked by some acid H positive. We can give it to H positive and it will become CH3 CH2 or CH and here CH3. So the positive sign is here. We can also use alcohol as a reagent. For example, if we have ROH, we can give it H positive to alcohol. It attacks and become ROH2. Here positive sign occur. This bond will break and we can get our electrolyte plus water in this way. These two reagents are also used. There are some defects of alkylation. We can also say drawbacks of alkylation. Drawbacks of alkylation. The first one is rearrangement. Rearrangement of reagent. Because of this rearrangement, we can change the page. Propene cannot act as alkylation. We can't make we can attach propane propyl halide on a benzene ring CH3 CH2 CH3 here bulk CH2Br. If we use AlBr2 or FeBl2, here we can get a positive sign, but it will rearrange to form CH3 CH. The positive sign become here, and here we have again CH3. This rearrangement cannot allow us to make to done our alkylation with a propane or propyl halide. The second drawback is dealkylation, and the third one is polyalkylation. So we can write as dealkylation and polyalkylation. Dealkylation means we can get our benzene ring after the reaction, after reacting it with alkyl halide as our Cl and plus CH2Cl goes to our reagent FeCl3, but in a product we got a benzene. It is termed as dealkylation, means our product is our reactant here, and sometime we will get our product as follows. Here ethylene, here it is also attached. It is termed as polyalkylation. it is also 45%, and we can get our real product as 30%, which is ethyl benzene. Here we can get 30%. So these are some drawbacks of alkylation. So now what we are studying. Today we are study about alkylation, and here is our reaction of benzene with alkyl halide. Is mostly used as alkylating agent, and AlCl3 as a catalyst, and it is also termed as Lewis acid. We can get our product with HCl and AlCl3. As we know that the aromatic reactions are held on some rules. So there are 3 steps for the mechanism of aromatic substitution reactions. The first one is making of electrophile. So for accomplish, we react RCl with AlCl3 catalyst, and we can get AlCl4 and R positive as our electrophile. The second step for the mechanism, for the proceeding of this mechanism, is making of pi and sigma complex. For accomplishing of these steps, we react our benzene or aromatic ring with our electrophile, and the first thing we can get is pi complex, which is a transition state, and it is denoted as follows. This will immediately turn into sigma complex intermediate. It is termed as intermediate because it is delocalized. It is somehow stable state. And the third step is removal of H positive from this sigma complex intermediate. This H removes because to regain aromaticity due to electron pulling effect of the ring, and due to the presence of this base which attacks on H positive, and we can get our product plus HCl plus catalyst return. Further, we had discussed that we can use other catalyst instead of AlCl3. We can use a FeCl3, BF3, TiCl3, ZnCl2, SnCl4, and we also discussed their behavior. It is the strongest AlCl3, then FeCl3, then BF3, then TiCl3, then ZnCl2, then SnCl4. So we can use other alkylating agents which are ethylene ethene and propene. Here if we give H positive to it, it will become this. And we can also use alcohol. If it attacks on H positive, it will become this one, and we can get our electrophile with a molecule of water. Further, we had discussed drawbacks of alkylation. The first drawback is rearrangement of reagent. If we use propyl halide as a reagent, that is propyl halide, if we use it as an agent of alkylation, it will rearrange to this one. So that's why rearrangement of reagent is first of the drawback, is one of the drawback of alkylation. The second drawback and third drawback is dealkylation and polyalkylation. First of all, dealkylation is the return of benzene ring if we react it with RCHCl2. Polyalkylation means the attachment of one or more alkyl group with benzene ring. In this way we can get our product is only 30%. So guys, if you liked that lecture, then thanks.